you guys at Terra specialize a lot in taking advantage of traditional computing and kind of allowing us to have simulations of quantum computing, that kind of thing. I guess maybe maybe explain a bit about Terra Quantum and
Yes.
how it fits into the broader quantum picture.
So Terra Quantum is a quantum technology company. We focus on all pillars of quantum technology in both hard and software development. Now, it always depends on who you talk to when you ask about what are the pillars of quantum technology. For us, it's quantum computing, it's sensing, it's imaging, it is cryptography. When we talk about hybrid quantum computing, so the um, idea here is really develop solutions, develop libraries that efficiently combine all the classical high performance computing plus quantum computers. Now, the terminology sometimes may be misleading. So everyone in the field currently uses hybrid. We all talk about integration, but then sometimes when you look at it, you find it's just a cloud provider that offers all the classical HPC that we all know so well, and all of a sudden an additional component, quantum processors. But how you combine it, how you efficiently leverage this new power, that is then up to the user. So for us, it's different. We think about integration and bringing quantum chips into our libraries. So think about maybe one part of a deep neural network, a fully connected layer, for example, that you express as a quantum circuit. Then a quantum circuit, by the way, is a set of gates that you stack together. And that is then generally how you express anything that you run on a universal or gate model quantum computer, hence the name gate model quantum computer. Now, you express that neural network in that form or this part of the neural network, then you still have to bring in the device. So the quantum device may use other gates. So they may not be the same as we have in our software. So we have to do a mapping. This integration into the software is a certain effort, but we do that. So it's not that we want the end user to worry about that. For the end user, in our view, the only thing you should worry about is what quantum chip I want to use. No matter the technology, no matter the topology of the chip, they should just switch a parameter. I want to use quantum chip A, it's a different parameter than using that other quantum chip B, and you can compare the performance. Still, the integration effort is on us. You have to do it. It's not something that can easily be done, but that's how we offer it, and that's how we see hybrid quantum software.
So
Yeah.
I have a couple of questions from what you just said. One of them is this: you said gate in there. So what
Yes.
does that mean, a gate in this context?
So when you think about all classical computing, so non-quantum computing, then the most fundamental level, we also use gates. We have the AND gate, the OR gate, XOR, not AND.
Gotcha.
In the end,
Gotcha.
we want to have a set of universal gates that can do any operation that we need. Now, the same thing we do in quantum computing. The difference is that because of how these gates are designed, there is in theory an infinite number of gates. We, of course, don't want to have an infinite number of gates, so we still limit it to certain gates that we use very often and efficiently to change the states of a quantum bit. So we do the same thing as we do in classical computing, but it's different because we're using quantum effects. So we have all this richness of quantum information where one bit can not only be in one state at a time, it can assume a superposition of states, which gives you much richer compute capabilities. So in that case, we apply still these gates on our quantum bits and apply a sequence of it. Then you call that quantum circuit, and that's the algorithm. So the whole artistry in quantum computing is very often to find the right set of gates, combine them efficiently, then also think about the properties of the device. So because these systems are very delicate, I cannot have an algorithm run for minutes. You only have nanoseconds, maybe microseconds on the chip. So it's a very small amount of time that I have to execute that circuit on the chip. So I must be very mindful how deep the circuit is. The more I interact with it, the more likely I mess the system up. So and that's what we prepare in our algorithms, predefined sets of gates mapped to specific devices. So an end user can run a hybrid quantum neural network and manipulate the layer still, manipulate the architecture, but doesn't have to worry about how to really access the device.
Very interesting. And so the different kinds of devices, you talked about how your software, Terra software, allows you to have the particular gates that you'd like on a given kind of chip. An interesting tidbit that you threw in there is that you only have very small amounts of time to run any kind of compute on the chip, which is, I mean, that's something quite different from classical computing. You can leave your classical computer running for months, sometimes without any issues. Whereas you said they're kind of nanoseconds or microseconds. So that's how quantum computing works all the time these days?
Yes, that's the challenge. So you really want to be fast in the execution of your circuit. There are different things to consider too. So if you have, you talk about coherence time. So this is the time that the quantum computer can hold this very delicate superposition. So all possible configurations of bits at once. So if you formulate the algorithm, then that would mean all possible solutions to a problem at one time. And when you make the system collapse, when you read out, so to say, then the whole artistry is getting the right solution out of all the many billions or sometimes trillions of solutions that you have available at a given time. So that's what we have to worry about, and then thinking about the depth of a circuit. So the deeper a circuit is, the more likely it is that the quantum computer, the system, collapses before the algorithm is completed. So ideally, I can limit my operations. Don't have too deep circuits. I can limit them in terms of the number of qubits that I access at once. So, for example, have a single qubit gate operate on the chip that causes less harm, so to say, than having an operation that goes over many qubits. Harm in the sense of risking collapse of that system.
Gotcha, gotcha, gotcha. And something that I'm familiar with from episodes like 721 with Amir Abbas is that a qubit is the quantum computing equivalent of a bit, but it has different properties than our classical bits, right?
Exactly, yes. So, still, when you think about the classical bits, and that's also to what you said before with a classical computer, I can run it for a month. I can even stop computation, read out an intermediate result, and then continue. This is all challenging with quantum computers and quantum bits. So, still, as you said, we have the smallest unit of information, the quantum bit in a quantum computer, but it's different. So, think about maybe an electron. Let's take the simplest atom that there is, a hydrogen atom. We have one electron in the orbit, and then we look at the electron only that has one quantum property that is called spin, and the spin can be up and down. And interestingly, as long as I don't look, and in that case it means interacting with polarized laser light, as long as I don't look, the states coexist. So it's up and down at once. And that's where the remarkable power, or one of the reasons why quantum computers are so powerful. So imagine you have two bits. So each of these two bits in the end will give you a zero or one. But as long as I don't look, it's zero and one at once. Means 2 to the power of 2 equals 4 possible configuration that that system can assume at once. If I have 3 bits now, I have 2 to the power of 3 equals 8. So this is very remarkable. It says that in a perfect quantum computer, anytime I add one quantum bit, I double its computational power. If I have 1000 or 1001, there's a significant difference. And now, in more practical terms, that means if I have expressed my solution in a way that I can embed it on a quantum chip, then or my problem, all possible solutions to that problem coexist. And now, what a quantum algorithm does usually is it makes all the solutions that you don't want unlikely to appear when you look at the system, when you measure it. um, they're never gone. So quantum computers are probabilistic systems. If you do everything correct in your algorithm, you can still get a nonsense solution. So that's why you don't only measure the system once, you do it 1,000 times. You're still very fast, still can be done in microseconds. And then you get 800 times agreeing solutions, 200 times some random solutions. So then you would do a majority vote and say that's the correct solution to the problem. And there's entanglement too. So I don't want to make this a physics lecture, but there are more quantum effects at play there.